Chapter 4 Modern Atomic Theory. To see a world in a grain of sand, and a heaven in a wildflower, hold infinity in the palm of your hand, and eternity in an hour. William Black, 1757 to 1827. Auguries of Innocence. Scientists attempt to understand the atom have led them into the unfamiliar world of the unimaginably small, where the rules of physics seem to be different from the rules in the world we can see and touch. Scientists explore this world through the use of mathematics. Perhaps this is similar to the way a writer uses poetry to express ideas and feelings beyond the reach of everyday language. Mathematics allows the scientists to explore beyond the boundaries of the world we can experience directly, just as scholars then try to analyze the poems and share ideas about them in everyday language. Scientists try to translate the mathematical description of the atom into words that more of us can understand. Although both kinds of translation are fated to fall short of capturing the fundamental truths of human nature and the physical world. The attempt is worthwhile for the occasional glimpse of those truths that it provides. And this chapter offers a brief qualitative introduction to the mathematical description of electrons and describes the highly utilitarian model of atomic structure that chemists have constructed from it. And because we are reading beyond the world of our senses, we should not be surprised that the model we create is uncertain and, when described in normal language, a bit vague. In spite of these limitations, however, you will return from your journey into the strange new world of the extremely small with a useful tool for explaining and predicting the behavior of matter. Because the modern description of the atom is closely tied to the concept of energy, we begin this chapter with an introduction to energy and its different forms. The presentation of information in this chapter assumes that you can already perform the tasks listed there, and you can test your readiness to proceed by answering the review questions at the end of the chapter. This might also be a good time to read the chapter objectives which precede the review questions. Section 4.1 Energy. Energy, it makes things happen. To get an idea of the role energy plays in our lives, let's spend some time with John, a college student in one of the coastal towns in California. He wakes up in the morning to a beautiful sunny day and decides to take his chemistry book to the beach. Before leaving, he fries up some scrambled eggs, burns some toast, and pops a cup of day-old coffee in the microwave oven. After finishing his breakfast, he shows his chemistry textbook into his backpack and jumps on his bike for the short ride to the seashore. Once at the beach, he reads 2 pages of his chemistry assignment, and despite the fascinating topic, gets drowsy and drops off to sleep. When he wakes up an hour later, he's real sorry that he forgot to put on his sunscreen. His painful sunburn drives him off at the beach and back to his apartment to spend the rest of the day inside. All of John's actions require energy. It took energy to get out of bed, make breakfast, paddle to the beach, and as you well know, read his chemistry book. John gets that energy from the chemical changes that his body induces in the food he eats. It took heat energy to cook his eggs and burn his toast. The radiant energy from microwaves raised the temperature of his coffee, and the radiant energy from the sun caused his sunburn. All chemical changes are accompanied by energy changes. Some reactions, such as the combustion of methane, a component of natural gas, release energy. This is why natural gas can be used to heat our homes. Some reactions absorb energy. For example, when energy from the sun strikes oxygen molecules O2 in the Earth's atmosphere, some of the energy is absorbed by the molecules, causing them to break apart into separate atoms. Before we can begin to explain the role that energy plays in these and other chemical reactions, we need to get a better understanding of what energy is and the different forms it can take. You probably have a general sense of what energy is. When you get up in the morning after a good night's sleep, you feel that you have plenty of energy to get your day's work done. After a long day of studying chemistry, you might feel like you hardly have the energy necessary to drag yourself to bed. The main goal of this section is to give you a more specific scientific understanding of energy. The simplest definition of energy is that it is the capacity to do work. Work, in this context, may be defined as what is done to move an object against some sort of resistance. For example, when you push this book across the table, the work you do overcomes the resistance caused by the contact between the book and the table. Likewise, when you lift this book, you do work to overcome the gravitational attraction that causes the book and the earth to resist being separated. When 2 oxygen atoms are linked together in a covalent bond, work must be done to separate them. Anything that has the capacity to do such work must, by definition, have energy. It takes work to move a brick wall. A bulldozer moving at 20 miles per hour has the capacity to do this work, but when the same bulldozer is sitting still, it's not going to get the work done. The movement of the bulldozer gives it the capacity to do work, and so this movement must be a form of energy. Any object that is in motion can collide with another object and move it. So any object in motion has the capacity to do work. This capacity to do work resulting from the motion of an object is called kinetic energy, which is abbreviated Ke. The amount of an object's kinetic energy is related to its mass and its velocity. If two objects are moving at the same velocity, the one with the greater mass will have a greater capacity to do work and thus a greater kinetic energy. For example, a bulldozer moving at 20 miles per hour can do more work than a scooter moving at the same velocity. If these two objects were to collide with a brick wall, the bulldozer would do more of the work of moving the wall than the scooter. If two objects have equal mass but different velocities, the one with the greater velocity has the greater kinetic energy. A bulldozer moving at 20 miles per hour can do more work than an identical bulldozer moving at 5 miles per hour. Energy can be transferred from one object to another. Picture the coin toss that precedes a football game. A coin starts out resting in the referee's hand. After the flips it, sending it moving up into the air. It has some kinetic energy that it did not have before it was flipped. Where did the coin get this energy? From the referee's moving thumb. When scientists analyze such energy transfers, they find that all of the energy still exists. The law of conservation of energy states that energy can be neither created nor destroyed, but it can be transferred from one system to another and changed from one form to another. As the coin rises, it slows down and eventually stops. At this point, the kinetic energy it got from the referee's moving thumb is gone. But the law of conservation of energy says that energy cannot be destroyed. Where did the kinetic energy go? Although some of it has been transferred to the air particles as it bumps into on its flight, most of the energy is still there in the coin in a form called potential energy, abbreviated PE, which is the retrievable stored form of energy an object possesses by virtue of its position or state. We get evidence of this transformation when the coin falls back down toward the grass on the field. The potential energy it had at the peak of its flight is converted into kinetic energy of its downward movement, and this kinetic energy does the work of flattening a flat blade of grass when the coin hits the field. There are many kinds of potential energy. An alkaline battery contains potential energy that can be used to move a toy car. A blade of pasta provides potential energy to allow your body to move. Knowing the relationships between potential energy and stability can help you to recognize changes in potential energy and to decide whether the potential energy has increased or decreased as a result of its change. Let's look at the relationship between potential energy and stability. A system's stability is a measure of its tendency to change. A more stable system is less likely to change than a less stable system. As an object moves from a less stable state to a more stable state, it can do work. Thus, as an object becomes less stable, it gains a greater capacity to do work and therefore a greater potential energy. For example, a coin in your hand, it is less likely to move than a flipped coin at the peak of its flight. So we say that the coin in the hand is more stable than the coin in the air. As the coin moves from its less stable state in the air to a more stable state on the ground, it collides with and moves particles in the air, a blade of grass. Therefore, the coin at the peak of its flight has a greater capacity to do the work of moving the objects and therefore a greater potential energy than the more stable coin in the hand. Anytime a system shifts from a more stable state to a less stable state, the potential energy of the system increases. We have already seen that kinetic energy is converted into potential energy as the coin is moved from the more stable position in the hand to the less stable position in the air. Just as energy is needed to propel the coin into the air and increase its potential energy. Energy is also necessary to separate two atoms being held together by mutual attraction in a chemical bond. The energy supplied increases the potential energy of the less stable separate atoms compared to the more stable atoms in the bond. For example, the first step in the formation of ozone in the Earth's atmosphere is the breaking of the oxygen-oxygen covalent bonds in more stable oxygen molecules, O2, to form less stable separate oxygen atoms. This change could not occur without an input of considerable energy. In this case, radiant energy from the sun. We call changes that absorb energy endomorphic or endogalactic changes. The attraction between the separated atoms makes it possible that they will change from their less stable separated state to the more stable bonded state. As they move together, they could bump into and move something such as another atom. So the separate atoms have a greater capacity to do work and a greater potential energy than the atoms in the bond. This is why energy must be supplied to break chemical bonds. When objects shift from less stable states to more stable states, energy is released. For example, when a coin moves from the less stable peak of its flight to the more stable position on the route, potential energy is released as a kinetic energy. Likewise, energy is released when separate atoms come together to form a chemical bond. Because the less stable separate atoms have higher potential energy than the more stable atoms that participate in the bond. The change from separate atoms to atom in a bond corresponds to a decrease in potential energy. Ozone O2, O3 forms in the stratosphere when an oxygen atom O and an oxygen molecule O2 collide. The energy released in this change comes from the formation of a new OO bond in ozone O3. We call changes that release energy exergonic or exogonic changes. Some bonds are more stable than others, the products of the chemical reactions that take place in an alkaline battery and in our bodies when the chemicals in a pasta are converted into other substances, have more stable chemical bonds between their atoms than the reactants do. Therefore, in each case, the potential energy of the products is lower than that of the reactants, and the lost potential energy supplies the energy to move a toy car across the carpet and propel a 4-year-old along behind it. The accepted SI unit for energy is the joule, abbreviated J, but another common unit is the calorie, abbreviated CAL. The calorie has been defined in several different ways. One early definition described it as the energy necessary to increase the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. There are 4.186 joules per calorie according to this definition. Today, however, the U.S. National Institute of Standards and Technology defines the calorie as 4.184 joules. For 4.184 joules and 1 calorie, or 4.184 kilojoules and 1 kilocalorie. The calories spoken of in the context of dietary energy, the energy supplied by food, are actually kilocalories, kcal, equivalent to 4,184 joules or 4.184 kilojoules. This dietary calorie is often written calorie using an uppercase C and abbreviated CAL with uppercase C. A meal of about 1,000 dietary calories provides about 4,184 kilojoules of energy. Table 4.1 in the textbook shows the energy provided by various foods. We will use joules and kilojoules to describe energy in this text. The image here shows some approximate values in kilojoules for the energy represented by various events. An object's kinetic energy can be classified as internal or external. For example, a falling coin has a certain external kinetic energy that is related to its overall mass and to its velocity as it falls. The coin is also composed of particles that, like all particles, are moving in a random way, independent of the overall motion or position of the coin. The particles in the coin are constantly moving, colliding, changing direction, and changing their velocities. The energy associated with this internal motion is called the internal kinetic energy. In object can be increased in three general ways. The first way is to rub, compress, or distort the object. For example, after a good snowball fight, you can warm your hands by rubbing them together. Likewise, if you hit on a metal with a hammer, it will get hot. And the second way to increase the internal kinetic energy of an object is to put it in contact with another object at a high temperature. Temperature is proportional to the average internal kinetic energy of an object. So higher temperature means a greater average internal energy for the particles within the object. The particles in a higher temperature object collide with other particles with greater average force than the particles of a lower temperature object. Thus, collisions between the particles of two objects at different temperatures cause the particles of the lower temperature object to speed up, increasing the object's energy, and cause the particles of the higher temperature object to slow down, decreasing this object's energy. In this way, energy is transferred from the higher temperature object to the lower temperature object. We call energy that is transferred in this way heat. The energy that is transferred through an object as from the bottom of a cooking pan to its handle is also called heat. Heat is the energy that is transferred from a region of higher temperature to a region of lower temperature as a consequence of the collision of particles. The third way an object's internal kinetic energy is increased is by exposure to radiant energy, such as the energy coming from the sun. The radiant energy is converted to kinetic energy of the particles in the object. This is why we get hot in the sun. Gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, and radio and TV waves are all examples of radiant energy. Although we know a great deal about radiant energy, we still have trouble describing what it is. For example, it seems to have a dual nature with both particle and wave characteristics. It is difficult to visualize both of these two aspects of radiant energy at the same time. So sometimes we focus on its particle nature and sometimes on its wave character, depending on which is more suitable in a given context. Accordingly, we can describe the light that comes from a typical flashlight either as a flow of about 10 of the 17th particles of energy leaving the bulb per second, or as waves of a certain length. In the particle view, radiant energy is a stream of tiny, massless pockets of energy called photons. The light from the flashlight contains photons of many different energies, so you might try to picture the beam as a stream of photons of many different sizes. It is difficult to picture a particle without mass, but that is just one of the problems we have in describing what light is. The wave view says that as radiant energy moves away from its source, it has an effect on the space around it that can be described as a wave consisting of an oscillating electric field perpendicular to an oscillating magnetic field. Because radiant energy seems to have both wave and particle characteristics, some experts have suggested that it is probably neither a wave nor a stream of particles. Perhaps the simplest model that includes both aspects of radiant energy says that as the photons travel, they somehow affect the space around them in such a way as to create the electric and magnetic fields. Radiant energy then is energy that can be described in terms of oscillating electric and magnetic fields, or in terms of photons. It is often called electromagnetic radiation. Because all forms of radiant energy have these qualities, we can distinguish one form of radiant energy from another either by the energy of its photons or the characteristics of its waves. The energies of the photons of radiant energy range from about 10⁻⁸ joules per photon for the very high energy gamma rays released in radioactive decay to about 10⁻31st joules per photon, or even smaller for low energy radio waves. The different forms of radiant energy are described on the next slide. One distinguishing characteristic of the waves of radiant energy is wavelength. The distance between two peaks on the wave of electromagnetic radiation. A more specific definition of wavelength is the distance in space over which a wave completes one cycle of its repeated form. Between two successive peaks, the wave has gone through all of its possible combinations of magnitude and direction and has begun to repeat the cycle again. Gamma rays with very high energy photons have very short wavelengths on the order of 10⁻14 meters or 10⁻⁵ nanometers. Short wavelengths are often described with nanometers, abbreviated small n, small m, which are 10⁻⁹ meters. In contrast, the radio waves on the low energy end of the AM radio spectrum have wavelengths of about 500 meters, about 1/3 of a mile. If you look at the energy and wavelength scales shown here, you will see that longer wavelength corresponds to lower energy photons. The shorter the wavelength of a wave of electromagnetic radiation, the greater the energy of its photons. In other words, the energy of a photon is inversely proportional to the radiation's wavelength. As image shown here, illustrates all forms of radiant energy are part of a continuum with no precise dividing lines between one form and the next. In fact, there is some overlap between categories. Note that visible light is only a small portion of the radiant energy spectrum. The different colors of visible light are due to different photon energies and associated wavelengths. Section 4.2 The Mysterious Electron. Where there is an open mind, there will always be a frontier. Charles F. Kettering, 1876 to 1958, American engineer and inventor. Scientists have known for a long time that it is incorrect to think of electrons as tiny particles orbiting the nucleus like planets around the sun. Nevertheless, non-scientists have become used to picturing them on this way. In some circumstances, the solar system or model of the atom may be useful, but you should know that the electron is much more unusual than that model suggests. The electron is extremely tiny, and model physics tells us that strange things happen in the realm of the very, very small. The modern description of the electron is based on complex mathematics and on the discoveries of modern physics. The mathematical complexity alone makes an accurate verbal portrayal of the electron challenging, but our difficulty in describing the electron goes beyond complexity. Modern physics tells us that it is impossible to know exactly where an electron is and what it is doing. As your mathematical and scientific knowledge increases, you will be able to understand more sophisticated descriptions of the electron. But the problem of describing exactly where the electron is and what it is doing never goes away. It is a problem fundamental to very tiny objects. Thus, complete confidence in our description of the nature of the electron is beyond our reach. There are two ways that scientists deal with the problems associated with the complexity and fundamental uncertainty of the modern description of the electron. The first is analogies. In order to communicate something of the nature of the electron, scientists often use analogies, comparing the electron to objects with which we are more familiar. For example, in this chapter, we will be looking at the ways in which electrons are like vibrating guitar strings. The second is probabilities. In order to accommodate the uncertainty of the electron's position and motion, scientists talk about where the electron probably is within the atom instead of where it definitely is. Through the use of analogies and the discussion of probabilities, this chapter attempts to give you a glimpse of what scientists are learning about the electron's character. Each electron seems to have a dual nature in which both particle and wave characteristics are apparent. It is difficult to describe these two aspects of an electron at the same time, so sometimes we focus on its particle nature and sometimes on its wave character, depending on which is more suitable in a given context. In the particle view, electrons are tiny, negatively charged particles with a mass of about 9.1096 times 10 to the minus 28 grams. In the wave field, an electron has an effect on the space around it that can be described as a wave of varying negative charge intensity. To gain a better understanding of this electron wave character, let's compare it to the wave character of guitar strings. Because a guitar string is easier to visualize than an electron, its vibrations serve as a useful analogy of the wave character of electrons. When a guitar string is plucked, the string vibrates up and down in a wave pattern. The figure here shows one way that it can vibrate. The 7 images on the left represent the position of the string at various isolated moments, and the final image on the right shows all those positions combined. If you squint a bit while looking at the vibrating guitar string, what you see is a blur with a shape determined by the varying intensity of the vibration along the string. This blur, which we will call the waveform, appears to be stationary. Although the string is constantly moving, the waveform is not, so this wave pattern is called a standing or stationary wave. Note that as your eye moves along the string, the intensity or amount of the string's movement varies. The points in the waveform where there is no motion are called nodes. Although many waveforms are possible, the possibilities are limited by the fact that the string is tied down and cannot move at the ends. In theory, there are an infinite number of possible waveforms, but they all allow the string to remain stationary at the ends. The figure here shows various allowed waveforms. The wave character of the guitar string is represented by the movement of the string. We can focus our attention on the blur of the waveform and forget the material the string is made of. The waveform describes the motion of the string over time, not the string itself. In a similar way, the waveform of the electron is represented by the waveform of its negative charge, on which we can focus without concerning ourselves about the electron's particle nature. This frees us from asking questions about where the electrons are in the atom and how they are moving, questions that we are unable to answer. The waveforms for electrons in an atom describe the variation in intensity of negative charge within the atom with respect to the location of the nucleus. This can be described without mentioning the positions and motion of the electron particle itself. The following statements represent the core of the modern description of the wave character of the electron. Just as the intensity of the movement of a guitar string can vary, so can the intensity of the negative charge of the electron vary at different positions outside the nucleus. The variation in the intensity of the electron charge can be described in terms of a three-dimensional standing wave, like the standing wave of the guitar string. As in the case of the guitar string, only certain waveforms are possible for the electron in an atom. Or we can focus our attention on the waveform of very charge intensity without having to think about the actual physical nature of the electron. Most of the general descriptions of electrons found in the rest of this chapter are based on the wave mathematics for the one electron in a hydrogen atom. The comparable calculations for other elements are too difficult to lead to useful results, so as you will see in the next section, the information calculated for the hydrogen electron is used to describe the other elements as well. Fortunately, this approximation works quite well. The wave equation for the one electron of a hydrogen atom predicts waveforms for the electron that are similar to the allowed waveforms for a vibrating guitar string. For example, the simplest allowed waveform for the guitar string shown here. The simplest allowed waveform for an electron in a hydrogen atom looks like the image shown below. The cloud that you see surrounds the nucleus and represents the variation in the intensity of the negative charge at different positions outside the nucleus. The negative charge is most intense at the nucleus and diminishes with increasing distance from the nucleus. The variation in charge intensity for this waveform is the same in all directions, so the waveform is a sphere. The allowed waveforms for the electron are also called orbitals. The orbital shown in here is called the 1s orbital. Theoretically, the charge intensity depicted in the last slide decreases towards zero as the distance from the nucleus approaches infinity. This suggests the amusing possibility that some of the negative charge created by an electron in a hydrogen atom is found an infinite distance from the atom's nucleus. The more practical approach taken by chemists, however, is to specify a volume that contains most of the electron charge and focus their attention on that, forgetting about the small negative charge found outside the specified volume. For example, we can focus on a sphere containing 90% of the charge of the 1s electron. If we wanted to include more of the electron charge, we enlarge the sphere so that it encloses 99% or 99.9% of the electron charge. This leads us to another definition of orbital as the volume that contains a given high percentage of the electron charge. Most of the pictures you will see of orbitals represent the hypothetical surfaces that surround the high percentage of the negative charge of an electron of a given waveform. The 1s orbital, for example, can either be represented by a fuzzy sphere depicting the varying intensity of the negative charge, or by a smooth spherical surface depicting the boundary within which most of the charge is to be found. Is the sphere the oneness electron? This is like asking if the guitar string is the blur that you see when the string vibrates. When we describe the standing wave that represents the motion of a guitar string, we generally do not refer to the material composition of the string. The situation is very similar for the electron. We are able to describe the variation in intensity of the negative charge created by the electron without thinking too much about what the electron is and what it is doing. So where is the electron and what is it doing? We do not really know, and modern physics tells us that we never will know with 100% certainty. However, with information derived from wave mathematics for an electron, we can predict where the electron probably is. According to the particle interpretation of the wave character of the electron, the surface that surrounds 90% of an electron's charge is the surface within which we have a 90% probability of finding the electron. We could say that the electron spends 90% of its time within the space enclosed by that surface. Thus, an orbital can also be defined as the volume within which an electron has a high probability of being found. It is not difficult to visualize a reasonable path for an electron in the 1s orbital, but as you will see later in this section, the shapes of orbitals get much more complex than the simple sphere of the 1s orbital. For this reason, we do not attempt to visualize the path an electron follows in an orbital. How should we picture the electron? Perhaps the best image is the one we used in Chapter 3, a cloud. Our interpretation of the nature of the electron cloud will differ, however, depending on whether we are considering the charge of the electron or its particle nature. If we wish to consider the charge of the electron cloud represents the continuous variation in the intensity of the negative charge. It is stronger near the nucleus and weaker with increasing distance away from the nucleus, like the fuzzy sphere picture in the last two slides. In the particle view, the electron cloud can be compared to a multiple exposure photograph of the electron. Once again, we must resort to an analogy to describe electron behavior. If we were able to take a series of sharply focused photos of an electron over a period of time without advancing the film, our final picture would look like the one shown here. We would find a high density of dots near the nucleus and the decrease in density with increasing distance from the nucleus, because there is a higher probability of finding the electron in the volume near the nucleus than in the same volume farther away. This arrangement of dots would illustrate the wave equation's prediction of the probability of finding the electron at any given distance from the nucleus. Just like the guitar string can have different waveforms, the one electron in a hydrogen atom can also have different waveforms or orbitals. The shapes and size for these orbitals are predicted by the material mathematics associated with the wave character of the hydrogen electron. This figure shows some of them. Before considering the second possible orbital for the electron of a hydrogen atom, let's look at another of the possible ways a guitar string can vibrate. The guitar string waveform shown here has a note in the center where there is no movement of the string. The electron wave calculations predict that an electron in a hydrogen atom can have a waveform called the 2s orbital that is analogous to the guitar string waveform shown here. The 2s orbital for an electron in a hydrogen atom is spherical like the 1s orbital, but it is a larger sphere. All spherical electron waveforms are called s orbitals. For an electron in the 2s orbital, the charge is most intense at the nucleus. With increasing distance from the nucleus, the charge diminishes in intensity until it reaches minimum at a certain distance from the nucleus. It then increases again to a maximum, and finally it diminishes again. The region within the 2s orbital where the charge intensity decreases to zero is called the node. The figure represents here shows cutaway quarter section views of the 1s and 2s orbitals. And the average distance between the positive charge of the nucleus and the negative charge of a 2s electron cloud is greater than the average distance between the nucleus and the charge of a 1s electron cloud. Because the strength of the attraction between positive and negative charges decreases with increasing distance between the charges, an electron is more strongly attracted to the nucleus and therefore is more stable when it has the smaller 1s waveform than when it has the larger 2s waveform. As you discovered in section 4.1, increased stability is associated with decreased potential energy, so a 1s electron has lower potential energy than a 2s electron. We describe this energy difference by saying the 1s electron is in the first principal energy level and the 2s electron is in the second principal energy level. All of the orbitals that have the same potential energy for a hydrogen atom are said to be in the same principal energy level. The principal energy levels are often called shells. The 1 in 1s and the 2 in 2s show the principal energy levels or shells for these orbitals. Chemists sometimes draw orbital diagrams such as the one shown here would like to represent the orbitals in an atom and arrows, which we will be adding later to represent electrons. The light representing the 2s orbital is higher on the screen to indicate its higher potential energy. Because electrons seek the lowest energy level possible, we expect the electron in a hydrogen atom to have the 1s waveform or electron cloud. We say that the electron is in the 1s orbital, but the electron in a hydrogen atom does not need to stay in the 1s orbital at all times. Just as an input of energy, a little arm work on our part can lift a book resting on a table and raise it to a position that has greater potential energy. So can the waveform of an electron in a hydrogen atom be charged from the 1s shape to the 2s shape by the addition of energy to the atom. We say that the electron can be excited from the 1s orbital to the 2s orbital. Hydrogen atoms with their electron in the 1s orbital are said to be in their growth state. A hydrogen atom with its electron in the 2s orbital is in an excited state. If you lift a book from a table to above the table and then release it, it falls back down to its lower energy position on the table. The same is true for the electron. After the electron is excited from the 1s orbital to the 2s orbital, it spontaneously returns to its lower energy 1s form. An electron in a hydrogen atom can be excited to orbitals other than the 2s. For example, an electron in a hydrogen atom can be excited from the 1s to a 2p orbital. There are actually 3 possible 2p orbitals. They are identical in shape and size, but it lies at a 90 degrees angle to the other two. Because they can be viewed as lying on the x, y, and z axis of a 3-dimensional coordinate system. They are often called the 2px, 2py, and 2pz orbitals. An electron with a 2p waveform has its negative charge distributed into lobes on opposite sides of the nucleus. The figure here shows the shape of a 2pz orbital. In order to more easily show how the 2p orbitals fit together, they are often drawn in a more elongated and stylized form, shown here. In a hydrogen atom, the average distance between the negative charge of a 2p electron cloud and the nucleus is the same as for a 2s electron cloud. Therefore, an electron in a hydrogen atom has the same attraction to the nucleus and the same stability when it has a 2p form as when it has the 2s form. Therefore, a 2s electron has the same potential energy as a 2p electron. These orbitals are in the same principal energy level because the shapes of the 2s and 2p electron clouds are different. We distinguish between them by saying that an electron with the 2s waveform is in the 2s sublevel, and an electron with any of the 3 2p waveform is in the 2p sublevel. Orbitals that have the same potential energy, the same size, and the same shape are in the same sublevel. The sublevels are sometimes called subcells. Thus, there is one orbital in the 1s sublevel, one orbital in the 2s sublevel, and 3 orbitals in the 2p sublevel. The following orbital diagram shows these orbitals and sublevels. The lines for the 2s and 2p orbitals are drawn side by side to show that they have the same potential energy for the 1 electron in a hydrogen atom. You will see in the next section that the 2s and 2p orbitals have different potential energies for atoms larger than hydrogen atoms. In the third principal energy level, there are 9 possible waveforms for an electron in 3 different sublevels. The 3s sublevel has 1 orbital that has a spherical shape like the 1s and the 2s, but it has a larger average radius and 2 nodes. Its greater average distance from the positive charge of the nucleus makes it less stable and higher in energy than the 1s or 2s orbitals. The calculations predict that the third principal energy level has a 3p sublevel with 3 3p orbitals. They have the same general shape as the 2p orbitals, but they are larger, which leads to less attraction to the nucleus, less stability, and higher potential energy than for a 2p orbital. The third principal energy level also has a 3d sublevel with 5 3d orbitals. 4 of these orbitals have 4 lobes whose shape is similar to the lobes of a 3d orbital. We will call these double dumbbells. An electron in a 3d orbital has its negative charge spread out in these 4 lobes. The fifth 3d orbital has a different shape as shown in here. When an electron in a hydrogen atom is excited to the fourth principal energy level, it can be in any one of 4 sublevels: 4s, 4p, 4d, or 4f. There is one 4s orbital with a spherical shape and a larger volume than the 3s. There are 3 4p orbitals similar in shape to the 3p orbitals, but with a larger volume than the 3p orbitals. There are 5 4d orbitals similar to but larger than the 3d orbitals. The 4f sublevel has 7 possible orbitals. Table 4.2 shows all the orbitals predicted for the first 7 principal energy levels. Notice that the first principal energy level has 1 sublevel, the second has 2 sublevels, the third has 3 sublevels, and the fourth has 4. If n is the number associated with the principal energy level, each principal energy level has n sublevels. Thus, there are 5 sublevels on the fifth principal energy level: 5s, 5p, 5d, 5f, and 5g. The 5s, 5p, 5d, and 5g orbitals have shapes similar to the 4s, 4p, 4d, and 4f orbitals, but they are larger and have higher potential energy. Each s sublevel has 1 orbital, each p sublevel has 3 orbitals, each d has 5 orbitals, and each f sublevel has 7 orbitals. Thus, there are 1 5s orbital, 3 5p orbitals, 5 5d orbitals, and 7 5f orbitals. The trend of increasing the number of orbitals by 2 for each succeeding sublevel travel continues for 5G and beyond. There are 9 5G orbitals with shapes more complex than the shapes of the 4F orbitals. In the next section, where we use the orbitals predicted for hydrogen to describe atoms of other elements, you will see that none of the non-elements has electrons in the 5G sublevel for their most stable state or ground state. Thus, we are not very interested in describing the 5G orbitals. Likewise, although the 6th principal energy level has 6 sublevels and the 7th has 7, only the 6S, 6B, 6D, 7S, and 7P are important for describing the ground states of the non-elements. The reason for this will be explained in the next section. None of the non-elements in its ground state has any electrons in the principal energy level higher than the 7th, so we are not concerned with the principal energy levels above 7. The orbital diagram in figure here shows only the sublevels or subcells and orbitals that are necessary for describing the ground states of the non-elements. Section 4.3 Multi-Electron Atoms. It is possible to solve the wave equation and determine the shapes and size of electron orbitals for the hydrogen atom and for any one electron ion, for example He plus or Li2 plus, but the calculations for any atom with 2 or more electrons are extremely complex. Fortunately, scientists have found that when they take the information derived from solving the wave equation for hydrogen atoms and apply it to other atoms, the resulting descriptions are sufficiently accurate to explain many of the chemical characteristics of those elements. Thus, the following assumption lies at the core of the modern description of atoms other than hydrogen. All of the elements have the same set of possible principal energy levels, sublevels, and orbitals that has been calculated for hydrogen. In other words, we assume that all atoms can have the sublevels and orbitals listed in the previous section. Now let us look at how the electrons of elements other than hydrogen are distributed in those hydrogen-like orbitals. Helium with atomic number 2 and 2 electrons is the next element after hydrogen in the periodic table. Both of helium's electrons are in the 1s orbital, and this allows them to be as close to the positive charge of the nucleus as possible. Even though the 2 electron charged clouds occupy the same space, the 2 electrons are not identical. The property in which they differ is called electron spin. Although the true nature of electron spin is uncertain, it is useful to think of it as if electrons can spin on their axis. We can visualize the 2 electrons in a helium atom as spinning in opposite directions. Arrows are added to an orbital diagram to show the distribution of electrons in the possible orbitals and the relative spin of each electron. The orbital diagram shown here for a helium atom. The orbital distribution of electrons can also be described with a shorthand notation that describes the arrangement of electrons in the sublevels without reference to their spin. This shorthand for helium's configuration is written 1s2 and is commonly called an electron configuration. The 1 represents the first principal energy level. The S indicates an electron cloud with a spherical shape, and the 2 shows that there are 2 electrons in that 1s sublevel. In the broadest sense, an electron configuration is any description of the complete distribution of electrons in atomic orbitals, although this can mean either an orbital diagram or the shorthand notation. The text will follow the common convention of referring to only the shorthand notation as an electron configuration. For example, if you are asked for an electron configuration for helium, you will write 1s2. If you are expected to describe the orbitals with lines and the electrons with arrows, you will be asked to draw an orbital diagram. Electrons do not fill the available sublevels in the order we might expect. Thus, to predict the electron configurations of elements larger than helium, we need a way of remembering the actual order of sublevel filling. Probably the least reliable method is to memorize the following list that shows the order of filling of all the orbitals necessary for describing the ground state electron configurations of all of the known elements. Instead of relying on memorization, you can use the memory aid shown here to remind you of the correct order of filling of the sublevels. The following steps explain how to write it and use it yourself. First, write the possible sublevels for each energy level in organized rows and columns. To do this, you need to remember that there is 1 sublevel on the first principal energy level, 2 on the second, 3 on the third, etc. Every principal energy level has an s orbital, the second principal energy, and all higher energy levels have a p sublevel. The d sublevel starts on the third principal energy level. The f sublevel starts on the fourth principal energy level, etc. Second, draw arrows like those you see here. Third, starting with the top arrow, follow the arrows one by one in the direction they point, listing the sublevels as you pass through them. The sublevels that are not needed for describing the known elements are enclosed in parentheses in figure shown here. Later in this section, you will see how to determine the order of filling of the sublevels using a periodic table. An atomic orbital may contain 2 electrons at most, and the electrons must have different spins because each s-level has one orbital and each orbital contains a maximum of 2 electrons. Each s-level contains a maximum of 2 electrons because each p sublevel has 3 orbitals and each orbital contains a maximum of 2 electrons. Each p sublevel contains a maximum of 6 electrons. Using similar reasoning, we can determine that each d sublevel contains a maximum of 10 electrons and each f sublevel contains a maximum of 14 electrons. We can now predict the electron configurations and orbital diagrams for the ground state of lithium, which has 3 electrons, and beryllium, which has 4 electrons. A boron atom has 5 electrons. The first 4 fill the 1s and 2s orbitals, and the 5th electron goes into a 2p orbital. The electron configuration and orbital diagram for the ground state of boron atoms shall be shown here. Even though only one of 3 possible 2p orbitals contains an electron, we show all 3 2p orbitals in the orbital diagram. The lights for the 2p orbitals are run higher on the page than the light for the 2s orbital to show that electrons in the 2p orbitals have a higher potential energy than electrons in the 2s orbital of the same atom. When electrons are filling orbitals of the same energy, they enter orbitals in such a way as to minimize the number of unpaired electrons, all with the same spin. In other words, they enter empty orbitals first, and all electrons in half-filled orbitals have the same spin. The orbital diagram for the ground state of carbon atoms is shown here. There are 2 ways to write the electron configuration of carbon atoms. One way emphasizes that the 2 electrons in the 2p sublevel are in different orbitals. Often, however, the arrangement of the 2p electrons is taken for granted, and the electron configuration shown here 1s2, 2s2, 2p2 is used instead. Unless you are told otherwise, you may assume that a complete electron configuration means a configuration written in the second form without the subscripts X, Y, and Z. The electron configurations and orbital diagrams for the rest of the elements of the second period show the sequential filling of the 2p orbitals. This figure shows how the electron clouds for the electrons of the atoms of first and second period elements are envisioned. Note that the electron chart waveforms for the electrons in different orbitals of each atom are superimposed on each other. The periodic table itself can be used as a guide for predicting the electron configurations of most of the elements. Conversely, the electron configurations of the elements can be used to explain the table structure and the similarities and differences that were the basis for the table's creation. The organization of the periodic table reflects the modern model model of the atom. For example, the highest energy electrons for all of the elements in groups 1 in 1A or 1A and 2 or 2A in the periodic table are in as orbitals. That is, the highest energy electrons for lithium, Li, and beryllium, Be atoms are in the 2s orbital, and the highest energy levels for sodium, Na, and magnesium, Mg, atoms are in the 3s orbital. This continues down to francium, Fr, and radium, Ri, which have their highest energy electrons in the 7s orbital. Therefore, the first two columns on the periodic table are called the S block. Because hydrogen and helium have their electrons in the 1s orbital, they belong in the S block too. All of the elements in the block with boron B, neon Ne, thallium Tl, and radon Rn at the corners have the highest energy electrons in p orbitals, so this is called the p block. The second principal energy level is the first to contain p orbitals, so atoms of elements in the first row of the p block have their highest energy electrons in the 2p sublevel. The highest energy electrons for 4 elements in the second row of the p block are in the 3p sublevel. This trend continues, so we can predict that the 81st through the 86th electrons for the elements thallium Tl through to radon Rn and added to the 6p sublevel. Moreover, we can predict that the new elements that have been made with atoms larger than element 112 have their highest energy electrons in the 7p sublevel. The last electrons to be added to an orbital diagram for the atoms of the transition metal elements go into d orbitals. For example, the last electrons added to atoms of scandium Sc through zinc Cn are added to 3d orbitals. The element cerium Y through cadmium Cd have their highest energy electrons in the 4d sublevel. The elements directly beyond them in rows 6 and 7 add electrons to the 5d and 6d orbitals. The transition metals can be called the d block. The section of the periodic table that contains the inner transition metals is called the F block. Thus, we can predict that the last electrons added to the orbital diagrams of elements with atomic numbers 57 through 70 would go into the 4F sublevel. Elements 89 through 102 are in the second row of the F block. Because the fourth principal energy level is the first to have an F sublevel, we can predict that the highest energy electrons for these elements go to the 5F sublevel. We can also use the block organization of the periodic table as shown here to remind us of the order in which sublevels are filled. To do this, we move through the elements in the order of increasing atomic number, listing new sublevels or sublevels as we come to them. The type of sublevel as P, D, or F is determined from the block in which the atomic number is found. The number for the principal energy level, for example, the 3 in 3p, is determined from the row in which the element is found and the knowledge that the S sublevel start on the first principal energy level, the P sublevel start on the second principal energy level, the D sublevels start on the third principal energy level, and the F sublevel start on the fourth principal energy level. We know that the first 2 electrons added to an atom go to the D1s sublevel. Atomic numbers 3 and 4 are in the second row of the S block. Look for them in the bottom half of figure shown here, signifying that the third and the fourth electrons are in the 2s sublevel. Atomic numbers 5 through 10 are in the first row of the P block, and the P sublevel start on the second energy level. Therefore, the 5th through 10th electrons go into the 2p sublevel. Atomic numbers 11 and 12 are in the third row of the S block. So the 11th and 12th electrons go into the 3s sublevel because atomic numbers 13 through 18 are in the B block. We know they go into a P sublevel because the P sublevels begin on the second principal energy level, and atomic numbers 13 through 18 are in the second row of the P block. The 13th through 18th electrons must go into the 3p sublevel. The position of atomic numbers 19 and 20 in the fourth row of the S block, and the position of atomic numbers 21 through 30 in the first row of the D block show that the 4s sublevel fills before the 3D sublevel. Moving through the periodic table in this fashion produces the following order of sublevels through 6s: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Note that atomic numbers 57 through 70 on the periodic table in figure shown here are in the 4f or portion of the table. It is a common mistake to forget that the 4f sublevel is filled after the 6s sublevel and before the 5d sublevel. In order to make the overall shape of the table more compact and convenient to display, scientists have adopted the convenience of removing the elements with atomic number 57 through 70 and 89 through 102, the latter being the 5f portion of the table from their natural position between the S and D blocks, and placing them at the bottom of the table. Electrons go into the 5f sublevel after the 7s sublevel and before the 6d sublevel. The periodic table is shown here shows how the blocks on the periodic table would fit together if the inner transition metals at the F block were left in their natural position. To write the complete electron configuration for an uncharged atom, follow these steps. Step 1. Determine the number of electrons in the atom from its atomic number. Step 2. Add electrons to the sublevels in the correct order of filling. Add 2 electrons to each S sublevel, 6 to each P sublevel, 10 to each D sublevel, and 14 to each F sublevel. Step 3. To check your complete electron configuration, look to see whether the location of the last electron added corresponds to the element's position on the periodic table. To draw an orbital diagram for an uncharged atom, follow these steps. Step 1. Write the complete electron configuration for the atom. This step is not absolutely necessary, but it can help guide you to the correct orbital diagram. Step 2. Draw a line for each orbital of each sublevel, reminding the complete electron configuration. Draw 1 line for each S sublevel, 3 lines for each P sublevel, 5 lines for each D sublevel, and 7 lines for each F sublevel. As a guide to the order of filling, draw your lines so that the orbitals that fill first are lower on the page than the orbitals that fill later. Label each sublevel. Step 3. For orbitals containing 2 electrons, draw one arrow up and one arrow down to indicate the electron's opposite spin. Step 4. For unfilled sublevels, add electrons to empty orbitals whenever possible, giving them the same spin. The arrows for the first 3 electrons to enter a P sublevel should each be placed, pointing up in different orbitals. The 4th, 5th, and 6th are then placed, pointing down in the same sequence so as to fill these orbitals. The first 5 electrons to enter a D sublevel should be drawn pointing up in different orbitals. The next 5 electrons are drawn as arrows pointing down and fill these orbitals again, following the same sequence as the first 5 D electrons. The first 7 electrons to enter an F sublevel should be drawn as arrows pointing up in different orbitals. The next 7 electrons are paired with the first 7 in the same order of filling and are drawn as arrows pointing down. We learned in Chapter 3 that the noble gases rarely form chemical bonds. This can now be explained in terms of the stability of their electron configurations. The formation of chemical bonds requires atoms to gain, lose, or share electrons, and the electron configurations of the noble gases displayed below are so stable that their atoms do not easily undergo any of those changes. The atoms of other elements other than hydrogen contain noble gas configurations as part of their own electron configurations. For example, the configuration of a sodium atom is the same as a neon's configuration with the addition of one more electron to the 3d 3s orbital. The 3s electron of sodium is much more important in the description of sodium's chemical reactions than the other electrons are. There are two reasons why this is true. We know from the stability of neon atoms that the 1s2, 2s2, 2p6 configuration is very stable, so these electrons are not lost or shared in chemical reactions involving sodium. These electrons are called the noble gas in the core of sodium. Another reason is that an electron in the larger 3s orbital is less strongly attracted to the nuclear charge than electrons in smaller orbitals in the first and second principal energy levels. As a result, the 3s electron is easier to remove. Because we are not as interested in the noble gas in the core of electrons for sodium atoms as we are in the 3s electron, sodium atoms are often described with the following abbreviated electron configuration shown here, in which Ni in brackets represents the electron configuration of neon. Sometimes the symbol for the noble gas is left out of abbreviated electron configurations, but in this text, all abbreviated electron configurations will consist of the symbol in brackets for the noble gas element at the end of the previous row, followed by the electron configuration of the remaining electrons. Abbreviated electron configurations are especially useful for describing the chemistry of larger atoms. For example, atoms of cesium Cs have one more electron than xenon Xc. Therefore, the 55th electron of a cesium atom is the only electron that is likely to participate in the formation of chemical bonds, because atomic number 55 is in the sixth horizontal row of the S block. The 55th electron must be in the 6s sublevel, making the abbreviated electron configuration for cesium atoms Xc in brackets 6s1. This is much easier to determine and much less time consuming to write than the complete electron configurations. If you are asked to write an abbreviated electron configuration, you can use the following steps. Step 1. Find the symbol for the element on a periodic table. Step 2. Write the symbol in brackets for the noble gas located at the far right of the preceding horizontal row on the table. Step 3. Move back down a row to the row containing the element you wish to describe, and to the far left, following the elements in the row from left to right. Write the outer electron configuration associated with each column until you reach the element you are describing. For zinc, we need to describe the 19th through the 30th electrons. The atomic numbers 19 and 20 are in the fourth row of the S block. So the 19th and 20th electrons for each zinc atom enter the 4s2 sublevel. The atomic numbers 21 through 30 are in the first row of the D block. So the 21st to the 30th electrons for each zinc atom fill the 3D sublevel. Zinc with atomic number 30 has the abbreviated configuration ARA in brackets 4s2 3d10.